Hey guys, tonight we begin far before daylight ever touched your skin, far before mornings had color, far before anything in your sky could be called sunrise. You are floating in a region of space so wide and cold that it almost refuses description, a dark nursery made of gas, dust, silence, and time. There is no fiery sun yet, no warm center to orbit, no blue earth waiting for oceans and weather and long naps on summer afternoons. There is only a giant cloud, loose and drifting, stretched across light years like a forgotten breath in the dark. Before you get cozy, take a moment to like the video and subscribe, but only if you genuinely enjoy spending time here with me. And wherever you are in the world, share your location and local time in the comments, because there is something comforting about knowing that while you listen in the dark, someone else is listening in early morning light. Let the world slow down for a moment. Let the fan murmur softly nearby, and let's slip into tonight's journey together. You drift there quietly, and the first thing that surprises you is how peaceful the beginning feels. People hear the word star and imagine noise, fire, drama, the kind of thing that deserves a very expensive movie soundtrack. But the sun does not begin as a blaze. It begins as a patience. It begins as a cold place where atoms wander with no special destination, where tiny grains of dust float through blackness and occasionally brush past one another like shy strangers in a dark hallway. This cloud is mostly hydrogen, the simplest element in the universe, with some helium mixed in and specks of heavier material left behind by older stars that lived, died, and scattered their remains into space long before our own sun was even an idea. That is one of the strangely comforting things about this story. The sun is not some isolated miracle dropped into emptiness. It is part of a long inheritance. The stuff that will someday glow in the sun's heart once belonged to older stars. The calcium in your bones, the iron in your blood, the oxygen you pull into your lungs without thinking, all of it comes from cosmic ancestors. Space has a habit of recycling with more elegance than humans do. At first, the cloud seems too spread out for anything much to happen. It is thin beyond anything you would call thin on Earth. Even the best vacuum cleaner in the world would feel embarrassed trying to tidy this place. But gravity does not care whether something happens quickly enough to impress you. Gravity is never in a rush. It only needs time, and out here time is basically free. Some slight disturbance passes through the cloud. Maybe a shockwave from a nearby exploding star. Maybe a pressure ripple moving through the region. Maybe just the cloud reaching the point where its own weight becomes too much to ignore. However it begins, the balance changes. And once that happens, gravity starts pulling matter inward. Slowly, then less slowly. A little more gas gathers here, which strengthens gravity there, which pulls in even more. The process feeds itself with quiet determination. You can imagine it as a kind of cosmic snowfall in reverse. Instead of drifting outward, everything begins leaning inward. Dust and gas sink toward denser knots inside the cloud. One of those knots will matter more than all the others to you, though no sign announces it yet. There is no glowing label that says future sun, please admire respectfully. There is just a region growing thicker, heavier, more crowded. As material falls inward, it starts to spin. This part feels almost unfairly graceful. In space, when a collapsing cloud shrinks, even a slight original motion becomes more noticeable. The same way a skater spins faster by pulling in their arms, this forming object turns more quickly as it contracts. What was once a broad, shapeless part of the cloud becomes a tightening, rotating structure. A dense center begins to form, wrapped by a flattened disk of leftover material. You are watching the outline of a solar system appear, though it still looks more like a ghost of one than the real thing. The central mass is not yet a star. It is a protostar, which sounds like something that should be carrying a clipboard and training for the full position. In a way, it is. It is a star in rehearsal. Gravity squeezes it tighter and tighter. As it contracts, the center heats up. That is a rule you see again and again in the universe. Squeeze gas hard enough and it gets hotter. No match is struck. No hand lights a flame. The heating comes from falling inward, from compression, from matter surrendering gravitational energy, and turning that energy into heat. So the young sun grows warmer, denser, brighter, but still not bright in the way you think of sunlight. It glows mostly from the heat of collapse. It is like a promise of fire, not the steady thing itself. Around it, the disk swirls with ice grains, rock particles, metals, and gas, all circling the center like ingredients laid out on a table before the actual meal begins. You are still in the age of becoming. And becoming, it turns out, is messy. The young sun is not born into a polished cosmic showroom. It forms inside turbulence. Clumps crash, merge, break apart. Magnetic fields twist through the gas. Jets of material can blast from the poles of the protostar, flinging some matter back into space while the rest keeps falling inward. It is orderly only from a great distance. Up close, it has the wild, half-finished look of construction. The solar system begins the way many beautiful things begin, not as perfection, but as chaos slowly learning a shape. You keep drifting nearer, and the center becomes harder to ignore. The protostar is now gathering most of the mass in this neighborhood. Almost everything that does not become the sun will still belong to the sun in one way or another. Its gravity will hold the future planets, moons, comets, and asteroids in an enormous family arrangement that lasts billions of years. Even before the sun shines as a true star, it is already becoming the ruler of a kingdom that does not yet know its own name. And still, the deepest magic has not happened. The core keeps heating, millions of degrees. The pressure rises to unimaginable levels. Hydrogen nuclei, which normally repel one another because they carry the same positive charge, are forced so close together that they can finally fuse. This is the threshold everything has been moving toward from the first faint collapse of the cloud. This is the line between almost a star and truly a star. You do not cross that line tonight. Not quite. You only feel how near it is. The great cloud that once wandered without urgency has given birth to a center that is close to ignition, close to becoming the source of all future dawns on Earth, close to powering oceans, leaves, weather, shadows, deserts, afternoon windows, and the golden light on someone's face you once loved and maybe never fully forgot. All of that is waiting inside this tightening sphere of gas. So you stay here a moment longer in the quiet before the fire, suspended in a darkness that is no longer empty, only expectant, watching gravity write the first sentence of the sun's life with extraordinary patience. And the more you look at it, the stranger and lovelier it becomes that something so warm, so familiar, and so constant begins in a place so cold and so still. The pressure keeps building in the young sun, and what looked calm from a distance turns out to be a very serious commitment to becoming something permanent. Gravity has done almost all the talking so far. It has pulled the cloud inward, tightened the spinning mass, shaped the disk around it, and heated the center through collapse alone. But gravity is not trying to make a warm, decorative lantern for the future Earth. Gravity is trying to crush matter inward as far as it can. It always does. Left alone, it would keep squeezing until the whole thing became denser, hotter, and more desperate. The young sun needs an answer to that pressure. It needs a way to push back. Deep in the core, the temperature rises toward about 10 million degrees Celsius, which is a sentence that sounds dramatic until you remember that your oven throws a tantrum at a few hundred. At these temperatures, the hydrogen nuclei in the core are moving so quickly, colliding so violently, that the usual electrical repulsion between them starts to lose its authority. Normally, two positively charged nuclei want nothing to do with each other. They resist. They keep their distance. Very relatable behavior, honestly. But under these crushing conditions, some of them get close enough for the strong nuclear force to take over, and once that happens, they fuse. That is the real beginning of the sun as a true star. It does not ignite the way wood ignites. No flame leaps up. No oxygen is needed. There is no crackling, no smoke, no campfire theatrics. Nuclear fusion is much stranger and much cleaner. In the sun's core, hydrogen nuclei begin a chain of reactions that eventually produce helium. Along the way, a tiny bit of mass is converted directly into energy. Just a tiny bit, but nature is very efficient with mass. Even a small amount, turned into energy through Einstein's famous equation, becomes enormous. So the sun begins to shine from the inside out. This moment is less like lighting a candle and more like switching on a self-sustaining engine. For a long time, gravity has been winning, pulling everything inward. Now fusion creates outward pressure. Radiation pushes against collapse. Heat supports the layers above the core. The young sun reaches a kind of balance, and that balance is one of the most important facts in its entire life. A star is not simply a burning ball hanging in space. A star is a long negotiation between inward gravity and outward pressure. The sun spends billions of years in that negotiation, holding itself together by balancing forces that would happily destroy one another if given the chance. And this is what makes the sun so steady. You wake up, the sunlight comes through a window, maybe too early if your curtains are weak, and your life has been betrayed by cheap fabric, and it feels ordinary. But that ordinary light depends on a balance maintained in the solar core every second. The sun is stable not because it is calm in the human sense, but because the violence at its center is so consistent that it creates reliability. The core becomes the heart of everything. It occupies only a fraction of the sun's total volume, but it is where the real power is made. Every second, the sun fuses hundreds of millions of tons of hydrogen into helium. The numbers are absurd in the way space numbers often are. They make your brain nod politely and then sit down in defeat. And yet the sun can keep doing this for billions of years because it started with so much mass. It has fuel to spare. Not infinite fuel, of course. Nothing in this story is infinite. That is part of what makes it beautiful, but it has enough to live a very long, very stable life. Once fusion starts, the sun changes from a protostar into a main sequence star. That phrase sounds almost disappointingly technical for something so grand, like calling a cathedral a large enclosed building with decorative ambition. But the main sequence is where stars spend the longest portion of their lives. This is star adulthood. This is the era of dependable power, when the sun settles into the role it will hold for most of its existence. The surrounding disk still circles it, and that matters more than ever now. The sun's light and solar wind begin shaping the leftovers of formation. Lighter gases are pushed and stripped from some regions. Heat changes what materials can survive at different distances. In the inner solar system, where temperatures are higher, rocky worlds will eventually take shape. Farther out, beyond colder boundaries, ices can remain solid, helping giant planets gather enormous envelopes of gas. The sun does not just switch on and illuminate a finished stage. Its birth actively influences what the planets can become. You can picture the newborn sun as both child and monarch at once, which is unfair to children and probably unfair to monarchs, but the image works. It is young, newly stable, not yet fully quiet in its behavior, and already setting the terms for everything around it. Its radiation floods the disk. Its gravity keeps order. Its magnetic activity can be fierce. The early sun was likely more active than the middle-aged sun you know today. Younger stars often spin faster and behave more energetically, with stronger flares and more intense outflows. So this is not a sleepy yellow lamp hanging politely in the dark. This is a newly established star, powerful, bright, and a little rowdy. And yet, even at its most intense, the sun is not unusual by the standards of the galaxy. That is one of the strangely humbling things about it. It is enormously important to you, to Earth, to every leaf and ocean and weather system and awkward family picnic. But in the Milky Way, it is considered a fairly ordinary star. Medium-sized, respectable, competent. The cosmic equivalent of someone who may not go viral but quietly keeps the whole neighborhood functioning. There are stars much larger, hotter, brighter, and shorter-lived. There are stars smaller, cooler, dimmer, and far more common. The sun sits in a very useful middle ground. That middle ground is the reason you are here. Massive stars burn through their fuel quickly and live dramatically short lives. Tiny red dwarfs can last for astonishingly long times, but their behavior and habitability questions get complicated. The sun, by contrast, offers a stable energy supply over billions of years. Long enough for Earth to cool, oceans to form, chemistry to get ambitious, life to begin, complexity to evolve, and eventually for one sleepy human to listen to a story about a star while lying under a blanket pretending they are absolutely going to sleep after this section. The light being produced in the core does not leap straight into space. That would be far too convenient. Instead, the energy begins an incredibly slow journey outward through the dense inner layers of the sun. Photons are created in the core, but they are immediately absorbed and re-emitted by surrounding particles, over and over again, in a chaotic random walk that can take an astonishingly long time before any of that energy finally reaches the surface. So even though fusion has started, the sunlight that will one day fall on Earth begins here in a kind of crowded delay, bumping through a star that is almost too dense to let its own energy escape efficiently. Still, the engine is on now, and everything that follows depends on this moment. The sun has crossed the line from collapse to balance, from almost star to star, from promise to presence. Gravity no longer writes the story alone. Fusion has joined in. The core glows with a power that will last for billions of years, and around that power, the future of the solar system begins arranging itself with increasing confidence. You remain there just long enough to feel the meaning of it. Not the violence, not the temperature, not the impossible numbers, but the quiet fact beneath them all. Every sunrise you have ever seen traces back to this turning point, this invisible change deep inside a forming star, when hydrogen first began to fuse, and the sun found a way to hold itself up against its own immense weight. With fusion steady in the core, the sun no longer feels like a question. It feels like a center. Not just physically, though of course that too, but almost emotionally, if a forming solar system can be said to have emotions, which it cannot, though it does have moods, and many of them are dusty. Around this young star, the wide spinning disk of leftover gas and dust keeps circling, no longer just a background detail, but the place where everything else begins to take shape. The sun has entered its role, and now the rest of the family starts assembling around it. The disk is enormous, much wider than the final arrangement of planets will seem from the inside. At first it looks smooth from far away, like a pale ring wrapped around the newborn sun. But close up, it is full of collisions, clumping, heat, drag, turbulence, and tiny local dramas that would each feel catastrophic if you were a dust grain, which thankfully you are not tonight. Small particles bump into one another and sometimes stick. That simple act, repeated enough times, changes everything. This is one of the most charmingly ridiculous parts of the story. Giant planets, moon systems, asteroid belts, all of it begins with dust learning how to cooperate. Minute grains collide and cling through electrostatic forces. Pebbles become larger clumps. Clumps become rocks. Rocks begin to gather into bodies large enough for gravity to matter more and more. There is no grand trumpet blast when a planet starts. It begins with persistence, with tiny repeated contacts, with material refusing to remain separate forever. Closer to the sun, the heat is intense. Only certain materials can stay solid there. Metals and rocky minerals survive better in the inner disk, while lighter volatile substances are more easily driven off. Farther out, where the temperatures are lower, ices can remain intact. That difference turns out to be crucial. It divides the solar system into neighborhoods with very different futures. The inner region becomes the home of smaller rocky worlds. The outer region, rich in ice and gas, can build much larger planets with deeper gravity wells and thicker atmospheres. So the sun does more than sit at the center. Its heat creates boundaries. Its light defines chemistry. Its radiation pressure and solar activity influence what remains where. The layout of the solar system is not arbitrary. It grows from the conditions set by this young star and the disk around it. The sun is shaping the kingdom not by issuing commands, but by existing with power in the middle of everything. As larger clumps form in the disk, they become planetesimals, early building blocks of planets. This is where the quiet beauty of dust turns into the rude physics of impact. These bodies collide, merge, sometimes shatter, sometimes scatter one another into new paths. It is messy work. There is no delicate little ribbon-cutting ceremony for each world. The early solar system is more like a construction site run by gravity, where nothing is labeled, everything is moving, and the safety inspector left millions of years ago. And still, out of that mess, order begins to emerge. In the inner solar system, rocky protoplanets grow by accreting more and more matter. Bodies crash together, pooling their mass, heating through impacts, differentiating as heavier materials sink inward and lighter materials rise. One of these worlds will become Earth. Another will become Mars. Another will become Venus. Mercury forms nearest the Sun, small and dense, like a survivor that learned to travel light. At this stage, none of them are the familiar worlds you know from textbooks or sky charts. They are hot, battered, changing, often molten, still deciding what they are. Farther out, beyond what is often called the frost line, things get even more dramatic. Here, ices can survive, adding extra solid material to the mix. That helps growing planetary cores become more massive more quickly. Once a core reaches enough mass, it can begin gathering huge amounts of hydrogen and helium from the surrounding disk. This is how the giant planets rise. Jupiter especially becomes the great heavyweight of the system, growing so large that it influences the destinies of many objects around it. Saturn follows, then the ice giants Uranus and Neptune in the colder reaches beyond. And all the while, the Sun remains the anchor of it all. Its gravity holds the disk in orbit. Its mass dominates the system so completely that almost everything else, taken together, is still tiny by comparison. More than 99% of the solar system's mass ends up in the Sun. That number is almost impolite. The planets get all the personality, all the press, all the dramatic close-up photography, and the Sun quietly keeps nearly all the mass like an introvert with terrifying leverage. As the planets grow, they begin to clear their orbits. Some material is swept up into them, some is flung inward, some is tossed outward, some never quite makes it and remains in smaller populations, becoming asteroids, comets, dwarf planets, and all the leftover wanderers that make the solar system feel more honest. Because that is another comforting part of this story. Creation does not use every scrap neatly. The solar system is full of leftovers. Belts of debris, distant icy reservoirs, irregular moons captured or battered into place. Order emerges, but not perfect order. The final structure still carries the memory of chaos. The Sun itself contributes to cleaning up the scene. The young star produces a stronger solar wind than the one you know today, a stream of charged particles flowing outward through space. Over time, this helps blow away the remaining gas in the disk, especially the lighter material that has not already been locked into planets. That matters because it sets a deadline. Planet formation cannot drag on forever in the same way. Once the gas is gone, the era of giant atmosphere building changes. The disk that once surrounded the Sun like a broad, luminous veil begins to thin, then fade. What remains is increasingly recognizable. Planets orbit the star. Smaller debris populations occupy particular regions. Moons circle planets. Resonances and gravitational relationships develop. Paths stabilize, though not instantly and not perfectly. The kingdom is still young, but now it has architecture. It is lovely to imagine this from far above, if space can be said to have an above. The Sun glows in the center, still more active than it will be later, surrounded by a gradually clarifying family of worlds. Mercury racing nearest, Venus wrapped in thickening atmosphere, Earth forming oceans much later but not yet, Mars cooling into rust-red quiet. Beyond them, the asteroid belt, full of pieces that never became a planet. Then Jupiter, huge and dominant, bending trajectories with its gravity like a giant moving furniture in a small room. Then Saturn with its future rings still taking shape through a longer story. Then the cold outer worlds, distant and blue-green and patient. And somewhere in all of this lies another subtle wonder. The sun's kingdom is not arranged for beauty, and yet it is beautiful. Orbital mechanics are not trying to impress you. Gravity is not making an aesthetic choice. But the result has rhythm. Worlds circle with periods and paths, each at its own pace, held by the same central star. Day and year, season and climate, eclipse and tide, much later all of these will depend on the arrangement set during this early era. You can also feel how narrow the margin is between this solar system and some other possible one. A little more mass here, a little less there. A migration slightly different. A collision that happens or does not happen. The family might have looked very different. Maybe a planet would never form. Maybe another would grow larger. Maybe Earth would fail to remain the kind of place where oceans and life can persist. The system you know is not inevitable. It is one successful outcome among many possible versions of a star, gathering a disk and turning leftovers into worlds. The sun, though, remains astonishingly dependable through all of it. While planets collide and migrate and sort themselves into rough order, the sun continues its balanced life at the center, fusing hydrogen, pouring out energy, shaping the environment simply by being what it is. It does not need to chase the planets or adjust their little personal dilemmas. Its gravity reaches everywhere. Its light reaches outward. It rules by presence. And there is something almost tender in the fact that this same star, which began as a cold concentration in a drifting cloud, has already done so much without ever moving from its center. It forms, it ignites, it clears, it heats, it holds. It creates the stage on which every later story will happen. Earth's oceans, moonlit nights, eclipses, sunflowers turning, human calendars, solar panels, lazy cats in windows. All of it depends on this early act of construction, when the sun built a kingdom out of dust, gas, and patience. The disk continues thinning. The glare of the sun falls more cleanly through the growing space between worlds. The family is not finished, but it is recognizable now, and as you look inward toward the young star, you begin to sense that the next mystery lies not in the planets circling it, but in the star itself. Because for all its outward influence, most of the sun's secrets are hidden inside, where the light begins a journey so slow and strange that even a star seems to struggle with the problem of letting its own brilliance escape. Inside the sun, the real surprise is not that it makes energy. The surprise is how difficult it is for that energy to get out. From far away, the sun looks effortless. It hangs there in the sky and sends light everywhere with the confidence of something that has never once doubted itself. It does not look delayed. It does not look crowded. It certainly does not look like a place where a photon can spend ages trying to escape like someone stuck in the world's most overheated train station. But that is exactly what happens. The energy born in the sun's core does not rush straight to the surface and then out into space. It begins an absurdly slow, tangled journey through layer after layer of dense solar interior. You move inward in your mind, past the bright surface you know from photographs and eclipses, past the visible features that humans can name, down into a place no eye can directly see. At the very center is the core, the deep engine room where hydrogen nuclei fuse into helium under crushing pressure and impossible heat. This is the one place in the sun where fusion happens at a meaningful rate. The temperature there climbs to around 15 million degrees Celsius. The density is staggering. Matter is squeezed so tightly that the core feels less like gas in the ordinary sense, and more like a packed, furious state of existence. This is where energy is born. When fusion reactions happen, they release energy in the form of gamma-ray photons and fast-moving particles, but those photons do not get a clear path outward. The sun's interior is too dense for that. A newly created photon can travel only a short distance before it hits a charged particle, gets absorbed, and then is re-emitted in a different direction. Then it happens again, and again, and again. The path outward is not a clean line. It is a random walk, a chaotic staggering drift through matter so crowded that almost every step gets interrupted. So when sunlight touches your skin on a warm afternoon, the energy itself may have been created in the core a very long time ago. The exact timescale is tricky because it depends on the model and the details, but the point is beautifully strange. The light that finally escapes the sun has spent an astonishing amount of time working its way outward. The sun shines steadily, but the energy you see is ancient by human standards, born deep inside long before it ever reached the surface. It is one of those facts that makes the ordinary world feel slightly haunted in the best possible way. Morning light seems immediate. In reality, it is patient beyond belief. Beyond the core lies the radiative zone, and this is where the slow struggle becomes almost comically stubborn. In this region, energy moves mainly by radiation, meaning photons are constantly absorbed and re-emitted by the plasma around them. Plasma, in case you want the quick version without a textbook trying to impress you, is matter heated so much that electrons are no longer neatly attached to atoms. The sun is mostly plasma, and that gives it strange electrical and magnetic behavior along with its intense heat. The radiative zone stretches outward through a large portion of the sun. It is calmer, in a sense, than the regions above it. Not calm in the way a lake at sunset is calm. More calm in the way an industrial furnace might be called stable by someone wearing very expensive protective gear. The particles here are packed tightly enough that photons cannot travel far freely. The result is a kind of endless ricochet. Every time a photon is absorbed and re-emitted, it may lose energy and reappear at a different wavelength. So the fierce gamma-ray energy created in the core does not stay gamma-ray energy all the way out. It gradually changes character as it moves through the star. This means the sunlight you know is not simply a beam shot directly from the core. It is the final expression of energy that has been processed, scattered, degraded, and transformed through countless interactions. The sun is not just producing light. It is slowly cooking it into a form the outer layers can finally release. That long travel time gives the sun a peculiar kind of thermal memory. The energy leaving the surface today reflects conditions deep inside from long ago, not the exact current state of the core in some immediate sense. The star is so large and dense that internal changes take time to work their way outward. This is one reason stars can remain stable for such long periods. They do not react like twitchy little devices. They respond with grand, slow dignity. As you move farther outward, the density drops and the story changes. You eventually reach the convection zone, the outer region where radiation is no longer the most efficient way to carry energy. Here the plasma itself begins to move in great circulating currents. Hot material rises toward the surface, cools, then sinks back down, only to be heated again and rise once more. It is like boiling water in a pot, except the pot is a star. The scale is monstrous, and nobody is making tea. This boiling behavior matters because it gives the sun much of its visible texture and some of its magnetic complexity. The convection zone is restless. It churns. It overturns. It carries energy upward not mainly by photons diffusing through matter, but by matter itself physically moving. The sun is not solid anywhere in the usual sense, so these enormous convective cells can form and shift with time, bringing heat toward the surface in a ceaseless pattern of rise and fall. You can begin to feel the sun as layered motion rather than as a simple glowing ball. The core fuses. The radiative zone traps and delays. The convection zone stirs and lifts. Each layer has its own behavior, its own role, its own rhythm. The result is the star you know, but the path from core to surface is much more involved than the smooth yellow circle drawn in children's books. Those books are doing their best, of course. They have limited space, and usually a smiling face on the sun, which is not scientifically ideal but does keep morale high. Eventually, the energy reaches the visible surface, the photosphere. This is the layer from which most of the sunlight you actually see escapes into space. It is not a hard shell. The sun has no solid crust to stand on, which is disappointing for anyone hoping to open an interstellar cafe there. The photosphere is more like the depth from which light can finally leave freely enough to travel outward without constant interruption. It is the apparent surface, the bright face of the star. And from there, at last, The light crosses space astonishingly fast. Once free of the sun, it takes about 8 minutes and 20 seconds to reach Earth. After all that time struggling to get from the core to the surface, the final trip across 93 million miles is almost insultingly quick. It is like spending years trying to leave a packed stadium and then catching an empty highway home in minutes. That contrast makes the whole thing lovelier. The sunlight warming your hands has a split personality. It is ancient in origin and immediate in arrival. Born in pressure and darkness, delayed by dense plasma, reshaped through the sun's layers, then released into open space where it races toward planets, moons, dust, atmospheres, eyes, leaves, oceans, windows, and anything else willing to catch it. You sit with that for a moment because it changes the way light feels. The next sunrise is no longer just the next sunrise. It is the visible end of a very long internal pilgrimage. Every sunbeam carries the history of a star that does not give up easily on its own brilliance. It fights through density, through scattering, through delay, and then finally spills into the solar system with the calm confidence of something that has earned its glow. And yet even the surface that releases this light is not smooth or quiet. Once you arrive there, expecting perhaps a neat shining layer after all that hidden complexity, you find instead a place that seethes and wrinkles and shifts without rest. The sun's visible face is alive with motion, and the closer you look, the more it becomes clear that this steady golden disk is hiding a deeply restless skin. The surface of the sun looks smooth only from a respectful distance, which is true of many dangerous things. From Earth, it appears as a clean, bright disk, stable enough to set clocks by and ordinary enough that most people stop thinking about it sometime around elementary school, unless they become astronomers or develop a personal grudge against summer. But when you move closer in your imagination and really stay there, the surface gives up that illusion almost at once. It is not smooth. It is not still. It is not a polished lamp glowing quietly in the dark. It is a living skin of motion, forever boiling, forever shifting, forever rearranging itself under the pressure of the furnace below. The layer you see is the photosphere, the visible face of the sun, and even calling it a surface is a little misleading. It is not a solid shell. There is nothing there you could stand on, unless your plan involved becoming a theory for a few seconds, and then a memory for no one. It is better to think of the photosphere as the level where the sun finally becomes transparent enough for light to escape into space. That is why it looks like a surface. It is the last bright layer your eyes can meaningfully see. And what a strange face it is. At first glance through powerful instruments, the photosphere has a grainy texture called granulation. These granules are not tiny in any human sense. Each one is often hundreds to more than 1,000 kilometers across. If one sat on Earth, it would not be called a granule. It would be called a crisis. They form because hot plasma rises from below, reaches the visible surface, cools, and then sinks again around the edges. So the sun's face is covered with countless bubbling cells, bright in the middle where hotter material rises, darker at the edges where cooler material falls back down. It is convection made visible. This means that the sun is quietly boiling all over, all the time. You can picture it like bread dough alive with heat, or like the surface of simmering soup if the soup were made of ionized gas and had no intention of being dinner. The granules appear, change shape, and vanish over the course of minutes. New ones take their place. The photosphere is never fixed long enough to become familiar. It is restless in a patient way, always moving yet never rushing. And then there are the sunspots, which have been noticed by human observers for centuries. They appear dark against the bright surface, like bruises or fingerprints, but they are not holes and they are not cool in the everyday sense. They are simply cooler than the surrounding photosphere, which is enough to make them look dark by contrast. A sunspot may still be thousands of degrees hot, which is a useful reminder that the sun has a very different understanding of the word cool than you do. Sunspots form where magnetic fields become intensely concentrated and twist up through the photosphere, suppressing the normal convective flow of hot plasma from below. With less hot material reaching the surface there, those regions are slightly cooler and dimmer. Often sunspots appear in pairs or groups, linked by magnetic structures, and they can last for days, weeks, sometimes longer, growing and shrinking as the sun's magnetic field shifts. The sun's magnetism is one of the reasons its surface is so fascinating. The star is not solid, and different latitudes rotate at different speeds. The equator turns faster than the poles. This differential rotation stretches and twists magnetic field lines over time, tangling them into more complex forms. The sun is constantly winding its own magnetic threads, and those threads can poke through the surface, loop above it, reconnect violently, and shape everything from sunspots to flares to great arches of glowing plasma. So the photosphere is not just boiling, it is magnetic theater. You begin to notice how strange the combination is. The sun looks calm from your backyard, yet up close it is a place where hot plasma rises and falls. Magnetic fields knot themselves into trouble and entire regions darken under forces you cannot see directly. It is not chaos exactly. It has patterns. It has cycles, but it is never settled. The sun is always doing something, even when it looks serene enough to bless a postcard. Above the photosphere lies the chromosphere, a thinner layer that becomes more obvious during a total solar eclipse, when the blinding photosphere is hidden and a reddish rim can briefly be seen. The chromosphere has a delicate beauty to it, a kind of glowing edge where the sun seems to whisper instead of shout. But even here the calm is deceptive. Jets of plasma called spicules rise and fall through this region, narrow and fast, like countless brief bursts from the solar surface. They shoot upward, fade, and are replaced by others. The sun does not merely glow, it sprays, it trembles, it breathes upward in fine fiery threads. Above that is the corona, the sun's outer atmosphere, stretching millions of kilometers into space. During an eclipse, it appears as a pale, luminous halo, one of the most beautiful sights in the sky, soft and ghostly and almost too elegant for something so violent. And the corona hides one of the great oddities of solar physics. It is much hotter than the visible surface below. The photosphere is around 5,500 degrees Celsius. The corona can reach millions of degrees. This feels backward because it is backward. If you move away from a heat source, common sense expects things to cool down. The sun, in one of its many small acts of cosmic arrogance, does not fully cooperate with common sense. Exactly how the corona gets so hot is tied to magnetic activity, wave heating, and the release of energy through tangled fields, though the details are still an active area of study. Which means that even after centuries of observation, the sun still keeps some of its methods to itself. That feels right. A star this central to your life should be allowed a few secrets. Looping through the corona are immense magnetic arches filled with glowing plasma, called coronal loops. These can tower high above the surface, tracing invisible magnetic field lines in graceful arcs. They look almost delicate in images, like golden ribbons suspended in the dark, but each loop contains matter at staggering temperatures and scales beyond ordinary human comparison. The sun has a talent for making huge things look decorative. And this is where your understanding of the sun's surface begins to deepen. The surface is not just the surface. It is the visible border of a whole connected system. Motions below churn upward into the photosphere. Magnetic fields twist through it and stretch into the atmosphere above. Sunspots mark tension. Loops reveal structure. Spicules leap. Granules boil. The corona glows with inexplicable heat. Everything talks to everything else. Even the sun's brightness is less constant than it appears. Over time, solar activity waxes and wanes in roughly 11-year cycles, with more sunspots and magnetic storms near solar maximum, fewer during solar minimum. The sun is stable in its total life as a star, but on the level of its surface behavior, it has moods. Not moods that care about your weekend plans, sadly, but moods all the same. This changing surface is one reason solar observation became so important in science. By studying sunspots and surface motion, astronomers learned that the heavens were not made of perfect, unchanging substance. The The sun showed marks, changes, irregularities. It rotated. It evolved. It had weather of its own, if you are willing to use weather very generously for a place where the forecast is always plasma with a chance of magnetic tantrum. And still, none of this breaks the sun's deeper reliability. That is the marvelous part. The surface can churn and flare and shift. The magnetic field can knot itself into elaborate trouble. Dark spots can bloom and fade. Yet day after day, century after century, the sun continues to shine with enough steadiness to support life on Earth. The turbulence does not cancel the constancy. It creates it in a larger, more honest form. So when you picture the sun now, you no longer see a flat yellow circle with some vague childlike glow around it. You see an immense convecting sphere whose visible face is alive with boiling cells, magnetic scars, rising jets, and arches of plasma. You see a star whose skin is always in motion, whose surface never truly rests, whose calm appearance is only the result of great distance and the limits of your eyes. And once you know that, it becomes easier to understand how the sun reaches beyond its own atmosphere. Because all this motion, all this magnetic tension, all this restless energy does not stay politely at home. Some of it breaks outward into space, flowing across the solar system as wind, storms, and charged particles that can brush past planets and rattle even worlds that orbit millions of miles away. What the sun does at its surface does not stay at its surface. That would be far too tidy for a star made of plasma and magnetic fields. The boiling face, the sunspots, the twisted loops, the hot outer atmosphere, all of it reaches outward into space. The sun does not end neatly where its bright disk seems to stop. It extends itself in a constant flow, a stream of particles and energy that moves across the solar system and touches every planet in one way or another. So even when the sun appears to sit quietly in the sky, it is continuously sending part of itself outward. This outward flow is called the solar wind, and the name makes it sound almost pleasant, like something that should rustle leaves and improve your mood on a balcony. It is not that kind of wind. It is a stream of charged particles, mostly protons and electrons, flowing from the corona into space in all directions. The corona is so hot that some particles gain enough energy to escape the sun's gravity altogether. Once they do, they spread outward through the solar system, carrying magnetic fields with them and filling interplanetary space with a moving solar atmosphere. So the planets do not orbit in empty space. They orbit inside the sun's extended breath. That is one of those facts that quietly changes your mental picture of the cosmos. Space around Earth is not blank. It is threaded with the influence of the sun. The solar wind sweeps outward, faster in some regions, slower in others, shaped by magnetic fields and coronal structures, interacting with planets, moons, dust, and the outer boundaries of the heliosphere, the vast bubble carved out by the sun's activity in the surrounding interstellar medium. In a sense, the solar system exists inside a great invisible weather system generated by its star. Most of the time, this flow is steady enough. Not calm exactly, because the sun never becomes that sort of creature, but steady in the way an ocean might be steady if you stop complaining about the waves. The solar wind varies, but there is a persistent outward streaming of particles. Earth's magnetic field helps protect the planet from the full force of it, guiding many charged particles around us rather than letting them strike the atmosphere directly. Without that magnetic shield, life on Earth would have had a much rougher relationship with the sun. Still, the protection is not perfect, and the sun is not always content with steady wind. Sometimes it has tempers. These tempers take several forms. One of the best known is the solar flare, a sudden release of energy from the sun's atmosphere caused by magnetic reconnection. That phrase sounds technical, but the idea is surprisingly visual. Magnetic field lines in the sun's atmosphere can become twisted and stressed, storing energy as the plasma moves below them. When those field structures suddenly rearrange and reconnect, they release enormous amounts of energy in a burst. That burst can accelerate particles, heat surrounding plasma, and produce radiation across the electromagnetic spectrum, from radio waves to X-rays. A solar flare is not the sun exploding. It is more like the sun snapping one of its own tangled magnetic cords and releasing the stored strain in a flash. The energy can be immense. In just minutes, a flare can release what would be an absurd quantity of power by any human standard. And because electromagnetic radiation travels at the speed of light, some of the effects of a major flare can reach Earth in about 8 minutes, crossing the same space that sunlight does. Then there are coronal mass ejections, which sound like paperwork but are much grander. A coronal mass ejection, or CME, is a huge cloud of plasma and magnetic field launched from the sun's corona into space. Not every flare produces one, and not every CME is aimed at Earth, thankfully. But when a large CME does head in our direction, it can interact strongly with Earth's magnetosphere. The result may be geomagnetic storms, disruptions to satellites, radio communications, navigation systems, and power grids. Beautiful auroras can flare far from the poles. Very occasionally, modern infrastructure remembers with some embarrassment that it is built under an active star. That is another lovely tension in this story. The sun gives life, but it is not gentle in every expression of its power. It is generous and unruly at once. You can think of the solar wind as the sun murmuring constantly, while flares and CMEs are the moments when it raises its voice. The murmuring shapes the space environment all the time. The louder outbursts remind planets that the star at the center is not just a light bulb. It is a magnetic, dynamic, unstable sphere whose atmosphere can suddenly fling matter across millions of miles. The Earth, fortunately, has several defenses. The atmosphere absorbs much of the sun's harmful high-energy radiation. The magnetosphere, generated by motions in Earth's liquid outer core, deflects many incoming charged particles. When those particles do get funneled toward the poles, they can collide with gases in the upper atmosphere and produce auroras. So the same solar activity that can threaten technology also paints some of the most beautiful lights in the sky. Green curtains, red glows, shimmering arcs, all created by particles from the sun meeting Earth's magnetic shield and atmosphere in a kind of elegant argument. The planets without strong global magnetic fields have a different experience. Mars, for example, once had a more protective magnetic environment early in its history, but today it lacks a strong global magnetosphere. That has made it more vulnerable to the stripping effects of the solar wind over long periods. The sun did not merely light Mars. It also helped change Mars. Atmospheres can be eroded. Surfaces can be exposed. Planetary histories can be altered by the steady and not-so-steady moods of a star. Even far beyond Earth, the sun's influence continues. The solar wind streams outward until it eventually slows against the pressure of interstellar space. That boundary region is complex, but the broad idea is that the sun creates a giant bubble around the solar system, the heliosphere, inside which solar particles and magnetic fields dominate. Only at the edge does the surrounding galaxy begin pushing back more strongly, so the sun's reach is not limited to the bright inner worlds. It stretches astonishingly far, past the outer planets and beyond, forming a vast domain around the entire planetary family. And yet, despite all this activity, the sun is still considered relatively well-behaved compared with many other stars. Some stars flare far more violently. Some are more erratic, more intense, less accommodating to the fragile business of long-term planetary habitability. The sun's storms matter deeply to us, but in the wider galaxy it still ranks as fairly moderate. Once again, it occupies that useful middle ground. Powerful enough to energize a solar system, stable enough to sustain life for billions of years, active enough to remain interesting. The rhythm of solar tempers also follows cycles. The sun's magnetic activity rises and falls over roughly 11 years, with more sunspots, flares, and coronal mass ejections near solar maximum, and fewer during solar minimum. These cycles are tied to the sun's magnetic field reversing polarity over a longer 22-year pattern. So even the sun's moods have a schedule, though not one polite enough to consult before affecting your satellite communications. For ancient humans, none of this was visible in detail. They could not see coronal mass ejections or map the solar wind, but they still sensed that the sun was not a simple object. Eclipses revealed its strange halo. Auroras hinted at invisible connections between sky and earth. Sunspots, when observed safely and indirectly, showed change on the face of the supposedly perfect heavens. Modern science added the mechanisms, but the feeling came earlier. The sun was alive with forces beyond ordinary sight. And that feeling remains worth keeping, because the sun becomes more interesting, not less, as it becomes more understandable. Knowing about solar wind and magnetic reconnection does not drain the mystery. It refines it. The mystery shifts from vague to a deeper one. How can something so violent also be so reliable, so unstable in detail, and yet so dependable in the long run, so capable of both nourishing forests and rattling power grids? You sit with that tension for a while. The sun is not a symbol of peace. It is a source of balance built from enormous internal struggle. It sends out light, heat, particles, storms, and magnetic structures across the dark. It fills the solar system with weather no human umbrella can help with. And still on Earth, beneath all that invisible activity, the larger gift remains the same. Daylight comes, oceans warm, winds move, plants turn light into food. Entire ecosystems rise and continue under the long reach of this star. Because beneath the storms and solar tempers lies the gentler truth that matters most to your own life. Nearly every ordinary comfort on Earth, every leaf, every meal, every breath linked to living green things, depends on sunlight finding its way from the sun to a small rocky planet at just the right distance. By the time the sun's power reaches Earth, it has already done something extraordinary just by arriving. It has crossed space, passed through the delicate balance of distance and angle, and touched a planet that happens to sit in one of the most fortunate neighborhoods in the solar system. Not too close, where the heat would be cruel and relentless. Not too far, where water would struggle to remain liquid and life would have a much harder time inventing itself. Earth lives in a narrow comfort zone, and the sun is the reason that comfort exists at all. You can start with the simplest truth. Almost everything alive on Earth depends on sunlight, either directly or indirectly. That is not poetic exaggeration. It is the plain architecture of the world. Plants, algae, and certain bacteria capture solar energy through photosynthesis, using it to build sugars from carbon dioxide and water. In the process, they release oxygen. So the food webs that support animals, forests, fisheries, grasslands, insects, birds, and eventually you, all begin with the sun pouring usable energy into the system. Even when you eat something that never saw daylight in any personal sense, the chain still runs back there. A loaf of bread, a bowl of rice, a piece of fruit, a grilled fish, a cup of coffee, all of it traces back through living systems powered by the sun. You are, in a very literal way, eating transformed sunlight on a regular basis, which makes lunch seem slightly grander than expected. It also means the sun is tucked quietly inside nearly every ordinary human routine. Breakfast on a table by the window, tea drying in fields, cotton growing in warm air, the wood of a chair formed from seasons of light and rain. Even fossil fuels, those buried leftovers of ancient life, are really old sunlight stored in chemical form by organisms that lived long ago. Humans have built entire industrial ages by setting ancient sunlight on fire and then acting surprised about the consequences. But before all the machines and smoke and arguments, there was the deeper gift. Sunlight made the planet lively. It does this not only by feeding plants, but by driving the great moving systems of Earth. The sun warms the atmosphere unevenly because the planet is curved and rotating. The equator receives more direct sunlight than the poles. Land heats differently from water. Day differs from night. Season differs from season because Earth's axis is tilted. Out of those differences come winds, pressure systems, storms, monsoons, trade winds, jet streams, the great circulating breath of the atmosphere. Weather is, in large part, the sun teaching air how to move. The oceans respond too. Surface waters warm, currents form, heat is transported across the globe. The sea becomes a slow memory of sunlight, storing warmth and redistributing it over time. Coastal climates are softened. Storm systems gather energy. Ice melts or grows depending on long balances of incoming and outgoing heat. The sun does not merely shine on Earth. It sets the whole planet into motion. And yet it does this with extraordinary delicacy. Earth receives only a tiny fraction of the sun's total output, just a small share of a star radiating in all directions. But that small share is enough. Enough to warm the surface, enough to sustain liquid water, enough to support a biosphere of dazzling complexity. This is part of the grandeur of the arrangement. The sun is unimaginably powerful, and Earth survives not because it captures a huge amount of that power, but because it captures just enough. That phrase, just enough, may be one of the quiet miracles of the universe. Too much more energy and Earth's climate history might have gone badly wrong. Too much less, and the planet could have remained frozen or much more hostile to complex life. In reality, Earth's climate has changed many times, dramatically at points, with ice ages, greenhouse phases, extinctions, recoveries, and all the complicated business of geology and atmosphere. But through all of that, the sun remained the central energy source. The terms shifted, the players evolved, the continents moved, the skies changed composition, and still the energy came from the same star. There is something deeply calming in that continuity. For billions of years, sunlight has arrived. It arrived on the early Earth when the surface was harsher, when the air was different, when life was microscopic and still experimenting. It arrived when the first cells learned to harvest light more effectively. It arrived when oxygen slowly built up in the atmosphere and changed the chemistry of the planet. It arrived when complex cells appeared, when multicellular life spread through the seas, when forests rose on land, when dinosaurs walked under daylight, when mammals hid and waited and eventually inherited more of the stage. It arrived for every age, every creature, every shoreline, every season no human ever saw. That long continuity makes your own experience of sunlight feel smaller and more precious at once. A patch of morning light on the floor is not just a pleasant detail in a room. It belongs to a stream of energy that has supported life for ages longer than imagination handles gracefully. The warmth on a winter wall, the brightness on a leaf after rain, the light caught in a child's hair, the gold over a late field, all of it is personal and cosmic at the same time. Humans, of course, built their lives around this long before they understood the physics. Agriculture depended on the sun before anyone knew what a photon was. Planting, harvest, migration, architecture, religion, calendars, labor, sleep, all of it leaned around daylight. You rose with the sun because there was little choice. You measured time by its motion because it was the most reliable thing in the sky. You feared drought when its heat seemed too strong, feared famine when its warmth seemed too weak or the seasons failed. The sun fed civilization and humbled it. And still does, just in more modern costumes. Solar panels are one of the clearest examples. After thousands of years of using sunlight indirectly through crops, wind, wood, and fossil fuels, humans finally learned how to catch solar energy more directly with technology. It is one of the rare moments in human history where the species looks almost elegantly sensible. The giant fusion reactor in the sky has been offering power this whole time, and eventually you begin putting dark rectangular panels on rooftops and saying, yes, perhaps we should accept the free beam. Even your sense of time and body rhythm is tied to the sun. The daily cycle of light and dark helps regulate circadian rhythms in humans and many other organisms. Sleep, alertness, hormone release, metabolism, mood. The body pays close attention to daylight whether your conscious mind is impressed by that fact or not. Morning light tells your brain that day has begun. Evening darkness cues the slow return toward rest. So the sun is not only out there powering ecosystems. It is also quietly helping govern the inner clocks of living creatures. That relationship can feel almost intimate. The sun is 93 million miles away, and yet it influences when you feel awake, when birds begin to sing, when flowers open, when insects emerge, when trees leaf out, when the air carries the promise of summer or the warning of winter. Distance does not cancel closeness when the link is this constant. And Earth has its own role in making sunlight livable. The atmosphere filters dangerous radiation, scatters blue light across the sky, softens transitions, helps retain warmth. Clouds reflect some sunlight back to space and trap some heat below. Water cycles moderate temperature. The magnetic field guards against much of the charged particle assault from the solar wind. The moon stabilizes Earth's axial tilt over long timescales, supporting more stable seasons. Life and planet and star are not separate stories stacked side by side. They are one long interaction. So when you ask why Earth lives in sunlight, the answer is not only because the sun exists. It is because the sun exists at the right scale, at the right distance for long enough, and because Earth became the kind of world that could answer that light with oceans. Weather, metabolism, memory, language, music, sleep, and wonder. You feel that answer settle slowly. The sun does not merely light the Earth. It feeds it, shapes it, times it, and accompanies it through every age. And long before science explained any of this in equations and models, humans felt the truth of it in more immediate ways. They looked up, watched the sun rise and vanish, feared eclipses, honored solstices, built myths around its return, and gave names to the deep dependence they could feel without fully understanding. Because once a star becomes this central to life, it never remains just an object in the sky. It becomes a story, a god, a symbol, a mystery, and eventually, with enough careful watching, a subject of science. Long before anyone understood fusion, plasma, magnetic reconnection, or the slow random walk of photons through the solar interior, people already knew the sun mattered more than almost anything else in their world. They knew it in their skin before they knew it in theory. They knew it in harvests, in shadows, in thirst, in migration, in ritual, in the relief of dawn after a dangerous night. The sun was never just seen. It was felt as a condition of life. That may be the most human part of this whole story. The sun became important to science only after it had already been important to everything else. If you place yourself among ancient people standing in a world without electric light, the sun immediately becomes larger in meaning. Night is not a cozy aesthetic with a dim lamp and a charging cable somewhere nearby. Night is uncertainty. It is cold, distance, predators, limits, and imagination doing whatever it likes in the dark. Then dawn arrives and the world returns. Shapes become clear. Roads exist again. Work resumes. Safety improves. Warmth spreads. In that setting, it makes perfect sense that the sun would feel sacred long before it felt astronomical. Across cultures, people gave the sun personalities, names, lineages, moods, and divine roles. In ancient Egypt, the sun was tied to Ra, the great solar deity who crossed the sky each day and journeyed through the underworld each night. In Greece, Helios drove the sun across the heavens, later sharing the imaginative space with Apollo, who became associated with light and order. In Japan, Amaterasu shone as a sun goddess central to myth and identity. In the Andes, the Inca honored Inti. In many cultures, the sun was not merely worshipped as power. It was woven into kingship, justice, fertility, timekeeping, rebirth, and cosmic order. And this was not foolishness waiting to be corrected by smarter centuries. It was human intelligence working with the tools it had. People recognized the sun's centrality with complete accuracy long before they understood its mechanism. Myth was an early language for dependence. That matters because it is easy to look backward and act superior, as if ancient people were just standing around assigning gods to bright things. But they were doing something deeper. They were building meaning around the most reliable pattern in their lives. Sunrise and sunset were not small details, they were structure. The sun was the great organizer of time. Days, seasons, solstices, equinoxes, planting cycles, migrations, ceremonies, all of them leaned on the sky. Monuments and cities often reflected that attention. Structures were aligned to solar events, especially solstices, with extraordinary care. Stonehenge is one famous example, but it is far from alone. Temples, ceremonial sites, and cities across the world were oriented in relation to sunrise points, sunset points, and seasonal changes. These alignments show more than reverence. They show observation. People watched carefully. They noticed where the sun rose in winter, where it rose in summer, how its path changed over the year, how light entered a doorway differently on one day than another. The sun became a calendar written in the sky. That same careful watching eventually led toward science. At first, human ideas about the heavens often placed Earth at the center, with the sun moving around it. This was understandable. From your daily experience, the sun clearly appears to rise, cross the sky, and set. If you had to make an early model with no telescopes and no modern physics, the geocentric picture is an honest first guess. It matches what it feels like. The ground seems still. The sky seems to move. Human intuition is not stupid. It is just local. Over time, though, observation grew sharper and explanations became bolder. Ancient astronomers in several cultures tracked the motions of the sun and planets with remarkable precision. The Greeks developed geometric models. Indian astronomers made major advances in mathematical astronomy. Islamic scholars preserved, refined, and extended earlier knowledge while producing their own careful observations and corrections. Chinese astronomers documented eclipses, sunspots, and celestial events over long spans of time. The story of understanding the sun is not a single straight line through one civilization. It is a long shared labor of watching the sky. Then comes one of the great perspective shifts in human thought. Copernicus proposed a heliocentric model in which Earth and the planets moved around the sun. It was not instantly accepted, partly because new ideas rarely receive flowers and applause, and partly because it asked people to surrender the comfortable sense that their world sat at the center of everything. But the heliocentric model explained planetary motions more elegantly. Kepler then improved the picture by showing that planets orbit in ellipses, not perfect circles, which was a rude but necessary correction to the ancient craving for heavenly perfection. Galileo, using the telescope, observed phases of Venus and sunspots, adding evidence that the old neat picture of unchanging celestial perfection had cracks all over it. Sunspots mattered more than they first seemed to. Those dark marks moving across the sun's face showed that the sun rotated. They also showed that the heavens were not flawless, crystal clear, eternal mechanisms untouched by change. The sky had texture. The sun had blemishes. The old idea of a perfect, incorruptible heaven began to lose its grip. That was a profound shift. The sun stopped being a pure symbol and became something with behavior. Then Newton entered the scene and gave the solar system a deeper kind of coherence. Gravity could explain why planets moved as they did. The same force pulling an apple down could keep Earth in orbit around the sun. The cosmos became unified in a new way. The sun no longer needed to be carried across the sky by divine horses, however stylish that image remains. It could sit at the center of a gravitational system governed by laws that worked everywhere. And yet even then, one major mystery remained. What was the sun actually powered by? This question troubled scientists for a long time. Chemical burning could not explain the sun's enormous output over geological timescales. Gravitational contraction could supply energy for a while, but not for the vast ages implied by Earth's history and biological evolution. The answer only emerged in the 20th century, when nuclear physics revealed that fusion in the sun's core could provide the needed power for billions of years. At that point, the sun changed again in human understanding. It became not just a bright object or a gravitational center, but a self-sustaining nuclear star, converting hydrogen into helium deep inside its core. That is such a beautiful progression. First the sun is a god, then it is a clock, then a moving object, then a center, then a physical system, then a star among stars, and through each shift it does not become smaller, it becomes deeper. Eclipses played a special role in this long fascination. A total solar eclipse can still make modern, fully informed adults behave with the awed silence of ancient witnesses because some experiences simply outrun vocabulary. When the moon covers the photosphere and the corona appears, the sun becomes uncanny. Daylight collapses, the sky darkens, the temperature drops, birds may quiet, the familiar order of things falters. For a few minutes, you see the sun differently, as structure rather than glare, as halo and shadow and impossible geometry. Historically, eclipses inspired fear, ritual, wonder, and eventually major scientific discoveries. During eclipses, astronomers could study the corona. In 1919, observations of starlight during a solar eclipse helped confirm Einstein's theory of general relativity by showing that light bent in the sun's gravitational field, which is a very satisfying human move, really. The universe stages a haunting celestial event, and humans respond by checking whether spacetime itself bends properly. The sun also became central to modern astrophysics because it is the only star close enough to study in such detail. Every other star is much farther away, a point of light even through powerful telescopes, but the sun gives you a laboratory on the scale of a star. By understanding the sun, humans learned how stars live, how they shine, how they age. The familiar star of daylight became the key to understanding the galaxy. So the sun through human eyes is many suns layered together, the life-giver of ancient fields, the divine presence in myth, the ruler of time, the object of careful records, the challenge to earth-centered pride, the marked and rotating sphere, the gravitational anchor, the nuclear star, the astrophysical model. Each age saw something real, even when incomplete. And perhaps that is the most human thing of all. You never see the whole truth at once. You approach it in generations, with stories first, then measurements, then better stories, then equations, then new mysteries. The sun has always been larger than the frame used to understand it. That remains true even now. Because for all the insight gained, the sun still belongs not only to science but to experience. It is still the light through leaves, the heat on stone, the brilliance that makes you squint, the disk half hidden by morning haze, the red evening glow over a city, the thing people photograph badly and feel deeply. It is still intimate and immense at the same time. And while humans have watched it with myth, reverence, fear, mathematics, and instruments, the sun itself has continued its long, stable life almost indifferently, shining through human centuries as if they were brief weather. Its middle age lasts far longer than any civilization, and even now it remains in that long, balanced era, quietly fusing hydrogen while the larger clock of stellar aging moves so slowly that a human life cannot feel it at all. The sun is, in the deepest sense that matters to life on Earth, middle-aged. That sounds almost funny at first. You are used to calling people middle-aged when they buy practical shoes, start making very firm comments about back support, and begin looking at weather as if it were a personal relationship. But for a star, middle age means something far grander and calmer. It means the sun has moved past the uncertainty of birth and the turbulence of youth, and it has settled into the long, stable stretch of its life when it knows exactly how to be itself. This stable period is the main sequence, the era when the sun steadily fuses hydrogen into helium in its core and maintains that precious balance between inward gravity and outward pressure. It is not an inactive phase. The sun is still pouring out unimaginable energy every second. Its surface still boils. Its magnetic field still twists. Solar wind still streams into space. But in the larger structure of its life, this is the long plateau, the broad, bright plain between beginning and ending. And it is very long indeed. The sun is about 4.6 billion years old, and it is expected to remain in this main sequence stage for roughly 10 billion years in total. So it sits somewhere around the midpoint of its most stable era, with about 5 billion years of similar life still ahead. That is such a huge amount of time that the mind has trouble holding it. Human history, all of recorded civilization, every empire, language, border, invention, war, poem, and lullaby, would vanish into a fraction too small to notice on that scale. The sun's middle age is not measured in generations or even species. It is measured in eons. That is one reason the sun feels so dependable. Its life unfolds at a pace that makes almost everything human seem brief and flickering. You wake, work, worry, celebrate, fall asleep, and the sun has barely advanced through a single cosmic heartbeat of its middle years. It shines across millennia with the same general steadiness, allowing living things to mistake permanence for personality. You begin to feel that the sun will always be there, not because it truly will, but because your own timescale is too short to catch it changing in any obvious way. Still, even a stable star is not static. At the core, hydrogen keeps fusing into helium. The helium ash gradually builds up in the center, and this changes the sun very slowly over time. As the core composition shifts, the sun's structure responds. The core contracts a little, heats up a little more, and fusion in the surrounding regions continues with slightly greater intensity. So the sun is not exactly as bright now as it was when Earth first formed. In fact, it has grown more luminous over its lifetime. Early in its history, the sun was fainter than it is today. This creates one of the interesting puzzles in Earth science known as the faint young sun paradox. Geological evidence suggests that early Earth had liquid water, even though the sun should have been dimmer back then. The likely answer involves greenhouse gases in Earth's early atmosphere helping trap enough heat to keep the planet warm. So even the sun's stable middle age contains gradual change, and Earth's own systems had to respond to that change to remain habitable. That subtle brightening continues. Over hundreds of millions and billions of years, the sun becomes a little more luminous, a little more intense. Not enough to matter dramatically on the timescale of your week, or your country, or probably your species' current emotional schedule, but enough that over geological time it shapes the future of Earth. Long before the sun reaches its final giant phase, increasing brightness will likely make Earth less hospitable. Oceans may gradually evaporate. Climate regulation may fail. The planet's surface may become far harsher. This is not tomorrow's problem, and it is not even humanity's likely direct concern unless your retirement plan is unusually ambitious. But it reminds you that stability in a star does not mean eternal sameness. It means slow transformation. And slow transformation is the theme of the sun's middle age. It is steady enough for complexity to flourish around it, yet changing enough that its future is always moving quietly toward a conclusion. The sun's constancy is real, but it is not frozen. It is more like the constancy of a deep river, always flowing in one broad direction even when the surface seems calm. On Earth, this long solar steadiness allowed life to become elaborate. Microbes evolved, oxygen accumulated, eukaryotic cells emerged, multicellular organisms spread, plants transformed continents, animals adapted, radiated, vanished, returned in new forms. The sun did not direct that story in detail, but it provided the long-lasting energy background that made the story possible. Evolution needs time, and the sun gave Earth an astonishing amount of it. This may be one of the most underrated facts about our star. The sun is not extreme in a flashy way. It is not among the largest stars or the hottest or the most spectacular, but it is spectacularly useful. Its mass, temperature, and longevity sit in a range that supports long-term planetary stability. It gives enough energy to sustain rich chemistry and active climate, but not so much that it burns through its life too quickly. It lives in the cosmic middle, and that middle turns out to be generous. You can feel the grandeur of that when you step back. Imagine all the stars in the Milky Way, each with its own mass, lifespan, and temperament. Some burn blue and furious, dying young in brilliance. Some glow dimly as red dwarfs for spans of time almost too large to imagine. The sun falls in between, and in that in-between space it offers a rare kind of hospitality. It is not immortal. It is not delicate. It is long-lived enough to be a reliable home star. Its middle age also has rhythm. The solar cycle rises and falls every 11 years or so. Magnetic polarity flips over about 22 years. Surface activity waxes and wanes. Sunspots come and go. Flares burst. Auroras brighten Earth's skies from time to time. All of these are like the small visible habits of a much larger stable life. They do not mean the sun is unstable in the stellar sense. They are the ordinary weather of its adulthood. If you want a human comparison, though all human comparisons break down eventually, the sun in this stage is less like a reckless youth and more like someone who has settled into a powerful routine. The daily work continues. The deeper structure holds. The visible details change, but the core identity remains. It knows how to shine now. It has been doing it for billions of years. And yet, the most poetic part may be this. The sun has no awareness of its own middle age. It does not reflect on time. It does not treasure its own stability. It does not admire the planets circling it or take pride in feeding forests and oceans. All the meaning comes from you, from life, from consciousness emerging on one small planet and realizing that its star is in the great calm center of its existence. That realization gives the sun a kind of borrowed intimacy. It becomes more than a ball of plasma because you are here to understand it, and because your own life is timed by its light. You grow up under its schedule. You feel seasons tilt beneath it. You mark birthdays by the Earth's completed circuits around it. Even your sense of a year is really the story of Earth returning to the same place in the sun's embrace. So when you say the sun is middle-aged, you are saying something scientific and something almost tender at once. You are saying that this star is in the long middle stretch of its existence, when it is most stable, most dependable, most able to support the intricate world that rose beneath it. You are saying that the great balancing act begun in its youth still holds. You are saying that billions of years from now it will change more dramatically, yes, but for now it remains what it has long been, a patient furnace at the center of a family of worlds. The clock, however, never stops. Helium continues building in the core. Hydrogen is slowly consumed. The balance holds, but not forever. The great stillness of middle age contains its own eventual ending, as all long, quiet things do. One day, far in the future, the core will run short of hydrogen fuel. The sun will leave this broad, stable plateau and begin the final transformation that has waited inside it since the first ignition. And when that happens, the star that once formed from a cold, drifting cloud, the star that built planets, fed Earth, and shone across civilizations, will swell into something larger, stranger, and more luminous than the sun you know now, carrying its long life toward its last great act. The sun's ending begins very quietly. There is no single dramatic morning when the solar system wakes up and realizes the star at its center has changed careers. The transformation starts deep inside, where the core gradually runs low on the hydrogen that has powered the sun for most of its life. For billions of years, fusion in the core has held the star in balance, gravity pressing inward, energy from fusion pushing outward. But eventually, the hydrogen in that central region becomes depleted. The core is left with more and more helium, and helium, at first, does not fuse under the existing conditions. So the central engine that kept the sun in its long, middle-aged steadiness begins to lose its grip. Gravity notices immediately. With less outward pressure from core fusion, the helium-rich core starts to contract. As it contracts, it heats up. That extra heat changes the surrounding layers. Hydrogen fusion continues, not in the very center now, but in a shell around the contracting core. And strangely, this does not make the sun smaller and quieter. It does the opposite. The outer layers begin to expand enormously. The sun swells. This is the beginning of the red giant phase, one of the most astonishing acts in the life of a star like ours. The sun that once sat in the sky as a stable golden disk will grow larger and larger, its outer atmosphere stretching outward, its surface cooling as it expands, its color shifting toward redder tones. It becomes a giant not because its core suddenly grows more powerful in the simple sense, but because the structure of the whole star rearranges itself in response to changes in the core. And what a rearrangement it is! The future red giant sun will become vastly larger than the one you know. Its radius may extend out past the current orbit of Mercury and likely beyond Venus. The exact details of how far its swollen outer layers reach, and exactly what happens to the inner planets, depend on complex interactions involving mass loss and orbital dynamics. But Mercury is doomed beyond argument, Venus almost certainly as well, and Earth enters a very grim neighborhood. Even before any possible physical engulfment becomes the question, Earth would long since have become uninhabitable. The oceans would be gone, the atmosphere transformed, the surface baked and stripped. The green, blue, clouded world you know would already be a memory of much earlier ages. It is a strange thing to imagine, and strangely calming too, once you stretch your mind to the scale involved. This is not destruction in the human sense. It is not sudden, malicious, or targeted. The sun does not turn against the planets. It simply continues being a star, and stars of this kind do not remain unchanged forever. The same physics that allowed the sun to shine for so long also requires that it eventually evolve. As the red giant phase deepens, the helium core keeps contracting and heating until it reaches temperatures high enough for helium fusion to begin. For a star the mass of the sun, that onset is surprisingly dramatic in the core itself, in an event called the helium flash. The name sounds like it should be visible as a grand cosmic fireworks display, but it happens deep inside and is largely hidden by the outer layers. Still, in physical terms, it is a major transition. The core becomes hot and dense enough for helium nuclei to fuse into carbon and oxygen. This gives the sun a temporary new balance. It settles for a while into another quieter phase, smaller than its maximum red giant size, burning helium in the core and hydrogen in a surrounding shell. But this stability is shorter-lived than the long main sequence age. The sun is now an older star, moving through later chapters more quickly. And when the helium in the core is exhausted, the cycle of imbalance returns. The sun does not have enough mass to keep fusing the heavier elements all the way up to iron the way massive stars do. It will never become the kind of star that explodes as a supernova. That is not its style. The sun's ending is gentler, though gentle is a very relative word when discussing a star unraveling itself across space. Instead, the outer layers become increasingly unstable and are eventually shed into space. The star pulses. It loses mass through powerful stellar winds. Layer after layer drifts away, expanding outward into the dark. What remains is not a ruined star exactly, but a beautifully exposed one. The sun casts off its outer atmosphere and creates a planetary nebula, a glowing shell of gas lit by the hot remnant core left behind. Planetary nebula is one of astronomy's more misleading names. It has nothing to do with planets in origin, just a historical accident from early telescopic observations. But the objects themselves are extraordinary. They can appear as luminous bubbles, rings, hourglasses, and delicate glowing clouds in space, colored by the gases they contain and the radiation exciting them. The future sun, after all its age and swelling and loss, will briefly create one of the most elegant sights in the galaxy. A final drifting veil of illuminated gas, the outer layers of a star gently shining before fading into the interstellar dark. And at the center of that glowing shell will remain the core itself, no longer supporting fusion in the way it once did. This remnant is a white dwarf. A white dwarf is one of the strangest kinds of object in the cosmos. It packs roughly the mass of the sun, or a large fraction of it, into a volume similar to Earth's. It is no longer generating new energy through sustained fusion. Instead, it shines because it is hot, because it retains the thermal energy of its former life, because all that compression and stellar history have left it glowing fiercely at first. Matter inside it is in a deeply unfamiliar state, supported not by ordinary gas pressure, but by electron degeneracy pressure, a quantum mechanical effect that stops the remnant from collapsing further under its own weight. So the sun's final long chapter is not a blaze, but an ember. The white dwarf will begin extremely hot, brilliant in its own compact way, but it will have no new nuclear fuel to draw upon. Over immense stretches of time, it will simply cool. Slowly, quietly, patiently. It will fade from white to redder tones and eventually, given timescales longer than the current age of the universe, toward a cold, dark state sometimes called a black dwarf, though the universe is not old enough for any true black dwarfs to exist yet. So the final light of the sun is not really a single last flash. It is a long diminishing glow, a fading memory of all the brightness that came before. There is something incredibly graceful about that ending. The sun begins in a cold molecular cloud, gathers itself under gravity, ignites, steadies, builds a system of worlds, feeds one of them long enough for life and mind to arise, grows older, swells into red giant grandeur, sheds its outer beauty into a nebula, and then settles into a compact white remnant, still shining but no longer burning in the old way. It is not an immortal object. It is a complete story. And that completeness is what makes the sun feel even more beautiful now, while it is still in its long, stable age. You do not lose wonder by knowing how the story ends. You gain it. Every ordinary sunrise becomes part of a finite brilliance. Every warm afternoon belongs to a star that had a beginning and will one day have only a fading afterglow. Its light matters more, not less, because it is not endless. The planets, too, inherit that ending in different ways. The outer worlds may continue circling the white dwarf remnant. Their skies will change beyond anything current weather has prepared them for. The inner solar system will be transformed beyond recognition. The architecture built in youth will remain in altered form, haunted by the absence of the star that once filled it so generously. Yet even in that altered future, the sun will continue to matter as history. The atoms in the nebula it sheds may one day join other clouds, other systems, other stars and worlds not yet formed. Matter moves on. The universe keeps reusing itself. That is perhaps the calmest truth of all. The sun's death is not the end of everything, only the end of the sun as the sun. Its material returns to the cosmos. Its long labor feeds later possibility. The same universe that made it from older stars will one day make other things from it. So when you picture the sun now, you can hold all its ages at once. The dark cloud, the protostar, the first fusion, the kingdom of planets, the boiling surface, the storms, the light on Earth, the myths, the long steady middle age, the swelling red giant, the brief glowing nebula, the white dwarf cooling in deep time, a whole life complete from first gathering to final light. And because this is the end of the story, the pace can soften now. The facts can loosen their grip a little. The scale can widen. The sun has carried you from cold dust to a fading ember, and nothing in that journey was wasted. Not the violence inside the core, not the storms in the corona, not the patient billions of years in which one small world learned to bloom under its light. So you let the image settle. You imagine the future white dwarf suspended in a quiet dark, no longer the broad warm presence of daytime, but a dense pale remnant, still holding the memory of its former radiance. Around it, the far reaches of the solar system continue in altered silence. The glowing shell of the old planetary nebula has already thinned and drifted away. The great red giant has passed. The bright middle age has passed. What remains is stillness, and a little lingering warmth, and the dignity of a star that completed its life exactly as its nature allowed. And then even that final glow continues to cool. Not suddenly, not sadly exactly, just slowly the way all truly large things happen, slowly enough that the word ending hardly feels right, more like settling, more like the universe lowering its voice, more like a fire that once lit worlds becoming a deep, quiet coal in the long night. So you breathe a little more easily here at the end. The sun does not vanish in panic. It does not break the story. It changes form, gives back its outer layers, and rests in the remnant of its own long work. The light that fed oceans and forests and human mornings becomes memory, then dimmer memory, then the possibility of future beginnings somewhere else in the dark. And you, for this moment, are still here in the era of sunlight, still living under the broad middle years of a patient star, still able to feel morning arrive in a room, or watch evening gold lean across a wall, or close your eyes and know that above the turning earth, the sun is there, balancing gravity with fire, holding its shape for a little while longer. That is enough. Now the images can soften further. The edges of planets can blur. The heat of the red giant can fade into distance. The white dwarf can become only a pearl of quiet light in a sea of black. The solar system can rest. The long story can fold itself gently closed, not with a slam, but with the hush of something vast finally at peace with its own completed arc. You do not need to hold all the numbers anymore. You do not need every temperature, every timescale, every layer of plasma and pressure. You can simply keep the feeling of it. A star was born from cold darkness. It learned to shine. It gave that light away for billions of years. And one day, very far from now, it will let the last of that light grow soft. So let the thought become lighter now, and slower and quieter. Let the sun return in your mind to its simplest form, not as a diagram or a model, but as warmth through a window, a pale dawn gathering behind curtains, a golden evening fading over roofs and trees. Let all the enormous machinery inside it become distant again. Let the core rest behind its layers. Let the storms go still. Let the surface smooth itself in imagination, just for this final moment. And as the world grows softer around you, you can feel how peaceful it is that even stars have lifetimes, that even great fires begin in silence and end in silence, and that in between they have time to illuminate whole worlds. Sleep can come easily here. The sun has done enough for one night.